Mr. Tarou, in this math lesson, we're going to be taking a look at graphing radical functions using transformations. And this is a very important concept. It's going to help us determine domain and range of a function, or actually determine if it's a function or relation. If we're doing application problems, or even some calculus problems, can be answered either very easily with a graph, or we can check the reasonableness of our solution by looking at what the picture tells us beyond just the numbers and the story maybe that's in an application problem. But at any rate, we're going to be starting with some kind of given function, some parent function. In this case, we're going to be working with square roots, and the fifth example is going to be dealing with a cubic function. We're also going to be looking at two different equations of both square roots and cubic functions and trying to describe what type of transformation would change the graph of one graph to the graph or give a graph of a new function. So with a given function f, they've got a couple of notations here. This textbook I'm teaching from currently uses like an f prime to show that there has been a transformation applied to a given function. That's fine for now. When you get into calculus, though, this is going to be indication or notation for a derivative, so not quite the same thing. So we'll be a lot of times using some kind of different letter. So g of x, some different function graph, is going to be created from the parent function graph with these transformations. Well, a coefficient at the beginning of whatever main math operation is in your equation, it could be a trig function, it could be a cube function, could be a square root function. If you have a coefficient out in front, that is going to be a vertical stretch. And if that coefficient of a is between 0 and 1, then actually what's happening is the graph is getting vertically compressed towards the x-axis. That's, of course, before there is any kind of vertical shift applied, because you multiply before you add or subtract with order of operations. And if your coefficient of a is greater than 1, then you have a vertical stretch from in reference to the x-axis. Now, if your leading coefficient is negative, that's going to take your graph and flip it over the x-axis. So like a standard parabola opens up, if you've dealt with those, and if you have like y equals negative x squared, it's going to reflect it over the x-axis and have it opening down. Then we have a coefficient that can be applied to your variable that's inside the main math function. And you're going to see that here with a 4 in front of the f and a 4 with the notation that is inside the main function. In this case, our parent function, our main function is that square root for the first few examples. If you have a coefficient in front of the x other than 1 inside the math function, and that's pointing to the name f, if b is greater than 0 or less than 1, you're looking at a horizontal stretch. And if b is greater than 1, as opposed to the multiple transformation that you have outside of the function, instead of an a value being larger than 1 being a vertical stretch, if a b value, a multiplication that's inside the math function, is greater than 1, that's going to be horizontal compression. That's going to be a little bit confusing, my explanation here, because we're dealing with square roots, and with radicals, your function, your book may be calling this value of b sort of another version of a vertical stretch. I saw that noted in the book that I'm making notes out of. It's a little bit misleading, because like when you're dealing, say, with trig functions, that multiplication that's inside the main math function, like a sine or a cosine, is always a horizontal compression. It's just the way the math works out with radicals that this value of b can be, in a way, looked at as a different version of a vertical stretch. We'll be talking about that as we go through these two examples here, g of x and h of x. And then finally, if you have a plus or minus, not finally, but almost, if you have a plus or minus inside the main math function, that's going to move the graph either left or right. There's a minus sign already in that standard form, so if it's x minus c, really that means your c is positive, because the negative is already in sort of this parent function standard form of expanded form of an equation. So c would be positive, and that's a shift to the right. If it's x plus c, it kind of seems like it should move the graph to the right, but it's actually move it to the left, because that means c would have to be negative to cancel out the minus that's already in our sort of standard form we're filling in here, and that's going to be a shift to the left. And then finally, you have another transformative value that is not inside the main math function, like b and c will be inside of our first four examples, the square root, but you have a plus d that's outside of the math function, a lot of times written at the end of the equation, that's going to shift the graph up or down. So we're going to look at the parent function of f of x is equal to the square root of x. Well, I'm not going to make a t-table, but maybe we don't know what the square root of x looks like. We have no plus or minus in front of this radical, so we're going to be looking at the principal root, the positive root. And if you think about x being 0, the square root of 0 is 0. If x is equal to 1, then the square root of 1 is 1. Each of these tick marks is 1 unit. I didn't write that down, but I probably should have. If x is equal to 2 or 3, I don't want to try and guesstimate where the decimal is in my graph, but if x is equal to 4, the square root of 4 is equal to 2, and the square root of, that would be 3, so maybe I do need to take a second. 2, 4. And I'm going to go off the screen here, but if I go all the way out to an x value of 9, the square root of 9 is going to be equal to 3. And this is roughly, that's roughly the sketch of our parent function. Now, if we look at g of x is equal to 4 times f of x, well, think about substitution. If it says 4 times f of x, well, 4 times, well, f of x is, I'm going to take f of x out and replace what it's equal to, the square root of x. Okay, so taking that function notation and actually writing what the function looks like, it's 4 times the square root of x. So again, thinking about, we're just moving to this idea of transformations. If x is 0, the square root of 0 is 0 times 4 is still 0. If x is 1, the square root of 1 is 1. And after you take or work through that main function that's in your equation, the square root, then at the end, when you're kind of sort of done, then you multiply by 4. So the square root of 1 is, or the square root of 1 is 1, and then multiply it by 4, you get 4. So what was 1 unit away from the x-axis is now 4 units away. That's where I said your multiple of a, if it's larger than 1, that's a vertical stretch away from the x-axis. Now I do say away from the x-axis, but if there was a plus or minus at the end, if there's a vertical shift, once you do that stretch, then you move it up or down. So you got to remember that those vertical stretches are applied before you add or subtract or move the graph up or down. So that's 2, and 2 times 4 is 8. So that's y is equal to 4 times the square root of x, or it is the graph of g of x. Now, h of x is a little bit different. H of x says that we're going to write the function f. Well, the function f is the square root of something. Okay, so f, the square root of something. Now, 4x is in there, not just simply x. So we're going to take out the value, the variable of x, and replace, what the function notation tells us to plug in, which is the 4x. Now, we can look at this in a couple of ways. We can look at it as my notes say in green, which is if b is greater than 1, then you have a horizontal compression. This 4 is going to take all of these points and move them closer to the y-axis with a factor, if you will, which is multiplication or division, of 4. So if b is equal to 4, that's obviously larger than 1, the distance that each of these points are along our parent function away from the x-axis, or y-axis, is going to come in not multiplying by 4, but by dividing by 4. So 1 unit away becomes 1/4 of a unit away. And like the square root of 4, or the square root of 4 gave us 2. Well, that point here of 4, 2 is 4 units away from the y-axis. So if I take that distance of 4 and divide it by 4, I get 1. And so on and so on. All these points are getting pushed in or pulled in towards the y-axis by dividing each of those distances by 4, and the graph is going to look, again, this is just a sketch, something to that effect. And with a lot of transformations, that is how you have to look at this transformation. And I always tell my kids, if you have a coefficient of x that's inside the main math function, it is a horizontal compression or stretch. But, with just how the square root function works out here and the fact that we have a couple of factors inside the square root, we can look at this as, let's just use a different color here for, well, it's still going to be the blue graph. I can pull this apart and say it's square root of 4 times the square root of x. Give each of those factors their own radical. And then the square root of 4 is equal to 2. So h of x, I think I might have called that g of x a second ago, but h of x now is equal to 2 times the square root of x. See, so in this particular case, and with the way the square root function allows us to work with the, the factors of that term individually, that 4, that b that's inside the radical can actually get pulled out and now be observed as a coefficient of a. So that's why the b inside our radical, this book is saying, is another form of a vertical stretch. But that's very, very, I think, dangerous, because with other applications, recognizing b as some form of a vertical stretch is going to get you in trouble and give you a wrong answer. But look at that. 0 times 2 is still 0, and 1 times 2 is equal to 2. So because we can bring out that multiple of 4, it can be represented as a transformation of a and b, a vertical stretch in this sense. We have j of x is equal to f of x minus 3. So again, f is the square root of something. That's what function f is, the square root of an independent variable. We're going to take out that independent variable x and plug in its place x minus 3. So we have j of x is equal to the square root of x minus 3. Well, that's a plus or minus that's inside the main math operation that we're interested in or working with in our equation. So that means that c is equal to 3, and that's going to move the graph to the right 3 places. Now finally, so here we have a different function. Y equals, or f of x is the cube root of x. Well, as long as we know what the parent function looks like, we can just apply the transformations like we did in the previous 4 examples. In the cube root, well, the cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is equal to 2. And therefore, the cube root of negative 8 is going to be negative 2, and the cube root of negative 1 is 1. So this is what our parent function looks like. Its domain and range is all real numbers, both for x domain and y for range. That's what the parent function looks like. Well, what do we have here? We have f prime of x, or f, not prime, but I'm thinking calculus, but some kind of transformation has been applied to f. We have a negative 1/2. We have the function f, which is the cube root of something. Inside of that function, we have an x plus 2 going in place of the independent variable x. And then minus 1. So we have a reflection over the y-axis. We have a horizontal compression of 1/2. So that means basically instead of going over 1 and up 1, I'm going to go over 1 and up just a half. And with the 8 and a 2, we have a shift. Okay, now this is x plus 2, but this plus 2 is inside our main math operation, which is the cube root function. So this is really like negative 1/2 times the cube root of x minus negative 2, and then finally we have a minus 1. So that's going to move the graph to the left 2 places, whereas as opposed to the negative 1 is going to move it down. See, the plus 2 kind of makes it seem like it should go to the right, but it's actually to the left. It's in that transformations inside the main math operation always seem to work in reverse. So this is a lot going on here. Well, the easy point is the 0, 0. That's going to get pushed left 2 and down 1. Don't have to worry about vertical stretches and horizontal stretches and reflections if we're talking about 0, 0, because nothing happens. Now, to the right, we were going up, but with the reflection over the x-axis, we're going to go down, and we're going to go down half as much. So instead of going to the right and up 1, we're going to go to the right and down just half of 1, which is 1/2. And instead of going left and down, we're going to go left and up. And I'll be right back. That was my wife bringing me lunch. That was very nice. So then instead of going to the right 8 and up 2, we're going to go to the right 8, which is going to negative 2 plus 8 is 6. And instead of going up 2, we're going to go down because of the reflection over the x-axis and go half as much. So we're going to go going down 1. And this will be a little bit of a challenge to draw. we're going to go off the scale anyway, because it's now even more stretched out, but it's going to look something, our transformed function is going to look something like, they'll go back up again, that's not right, something to that effect. And that is how you graph, well, actually all functions using transformations, but in this case specifically square roots and cube roots. Now let's move on to looking at, comparing just algebraically, seeing what the equations are between, what's the transformations between two given functions. Alrighty then, moving on from graphing, describe how each graph represented by f of x would be transformed to create g of x. Okay, well, over here we've got, those square root functions we just looked at, and we have a -2 that is inside the math function. Those are the shifts either left or right. And it's x minus c, which means our c is a +2. That's going to shift our graph to the right 2 units. And it's going to, with a plus or minus that's not in our main math function, which again is that square root here, that's going to shift the graph either up or down. It's a -1, it's going to shift the graph down 1 unit. Now, just with that, if we know the domain and range, if we know the domain of the square root y equals the square root of x is from 0 to infinity, then if we move the graph 2 units to the right, I know at least one way of thinking about this, that the domain is going to be from 2 to infinity. Instead of starting at 0, it starts at 2. And if the range was, because we have no plus or minus, so that we're only talking about those positive principal roots. If we went from 0 to infinity for the range and we move the graph down 1, we're going to go from -1 to infinity. Now with number 7, or example number 7 here, we had 4 graphs of the square root, 1 of the cubic root, and then 6 and 7. We look here that function f of x has already got some transformations in it. It was already moved to the right 3 units and up 4. So kind of like instead of that center point being at 0, 0, that center point, if you will, is at 3, 4. Well now, instead of shifting, at least from the parent function f of x, that f was 3 units to the right. Well, now I want a new function that's only 1 unit to the right as far as the parent function is concerned. If I don't want to go that far to the right, 3 units, I only want to go to the right 1 unit. Well, to get from f, to g, we're looking at, right? Now, you can just go, yeah, that was shifted 3 to the right. This is only shifted 1 to the right from the parent function of y is equal to the cube root of x. So to go from f to g, you got to go left 2. Now, again, from that parent function, f was moved up 4, but I want to actually not go up 4, but down 2. So what's the difference between from sort of that 0, 0, remember that parent function going through 0, 0, instead of going up to 4 for function f, we want to go down to -2 for function g. Well, that means I'm going to have to push this original function f with the transformations already in there down 6 units to get from 4 to -2. And if you remember from that previous example of graphing the cubic function where it goes left and right and up and down forever, the domain for all of your cubic functions are going to be all real numbers. That's the answer for the domain and the range. So the transformation doesn't affect the domain and range like it does with your square root function. Now over here, we have a value which is negative, that reflection over the x-axis. And we have something going on here with b. So in our first example, our value of b is 2. So at least from the original parent function y equals the square root of x, this has a horizontal compression by a factor of 2, and this has a horizontal compression by a factor of 8. And whereas shifts left and right and up and down, left and right and up and down, are about addition and subtraction, stretches, vertical stretches and compressions, and horizontal stretches and compressions are about factors or multiplication / division. So what multiple, or dividing is multiplication, what multiple gets you from 2 to 8? Well, 4. So if you want to make function f look like function g, you're going to need to increase that horizontal compression by a factor of 4. And again, that means you're going to move all the points horizontally towards the x-axis 4 units, y-axis 4 times closer. Again, well, before there's any kind of horizontal movement. Now again, because of the fact that with the radicals, we can look at the factors, kind of give their factors their own square root. This can be written as the square root of 2 times the square root of x. Now we have an a value, which is the square root of 2, not a b value, which is just 2. And we have negative the square root of 8 times the square root of x. Well, that can be written as, or can be written as, negative square root of 4 times the square root of 2 times the square root of x, giving us a final answer. Sorry about scribbling all over the place here now. The square root of 4 is equal to 2. Now, with us being able to break and give each factor its own square root, and taking the square root of 8, which is 2 square root of 2, and the original function is square root of 2 times the square root of x, somebody else can say, instead of applying a horizontal compression by a factor of 4, move all the bring in horizontally the points by dividing all those distances by 4, someone else can say that to create g from f, you need to, again, still reflect it over the x-axis, but apply a vertical stretch, which has a factor of 2. I got one more example coming up right now. And for our last 2 examples, we're going to be writing the equation of each function by transforming the equation as described. We're not sketching based on transformations. We're not trying to pull those transformations out of a given function. We're trying to come up with a new equation. So we have f of x, which is negative square root of x plus 2. So function f actually already has some transformations in it. Move to the left 2 and a reflection over the x-axis. I want to take this function and move it from the original parent function of y equals square root of x. Instead of moving it, like from f, which has already been moved left 2 units, I want to move f even 2 units farther to the left from the parent function, and then move it up. So from that original parent function, y equals square root of x, don't move just left 2, move to the left 2 more. So basically move to the left 4 units. Right? It's x minus c. So we get that plus 4 in there. And then up 1. That's how vertical slides or transformations are outside the main math function. They don't kind of work in reverse, sort of like that left-right stuff does. And there is our transformation for A, our new equation. Now in B, I want a stretch by a factor of 2. That's pretty simple. The vertical stretch, and right vertical, but the vertical stretches are about A, and that's right out in front of the main function. So that part is actually a pretty simple part of our solution here. And then things get a little bit tricky. It doesn't seem like it should be, but it reflected over the y-axis. Well, a reflection over the y-axis is caused by a coefficient of b, which is negative. Now, our original page of notes said that b, it was a, f, parentheses, b, parentheses, x minus c plus d. Now, I said, I like this format a lot of times, and this is not the format that my pre-calculus / trig book uses. And it says bx minus c. There's no parentheses there. Well, in the format given to us for a transformed function, b is outside of the parentheses, and b is, well, if I want to reflect over the y-axis, negative. So is it negative x plus 2? And by the way, I'm reshooting the scene because that's what I wrote. Even though I made my notes and I checked everything, that's what I wrote recording the videos. So this is tricky because it's wrong. If I look at the original function here with a shift left and a reflection over the y-axis from the parent function, well, we're talking about y is equal to square root of x. That looks sort of like this. This is with left 2 and with a reflection over the x-axis looks like, let's try that again. this way. Reflection over the x-axis and to the left. Yeah, okay, now we're ready. I want to take this graph and reflect it over the y-axis. Well, what was to the left is now going to be to the right. And what was to the right of the y-axis is now going to be to the left. I need a graph that looks like that. I need a graph that's, you know, instead of like the standard square root function opening or going towards the right, I want it going to the left. Well, that indicates that. But this plus 2 shows that from my original parent function, take that square root function, reflect it over the y-axis, and shift it to the left. But I don't need it to start at -2. I need it to start at +2. So really, this negative b is best to come into the function without those parentheses. And that actually helps me see why my pre-calculus book I teach from doesn't include the parentheses inside the transformed sort of general form of that equation, even though I do prefer that. If I take this negative and I factor it back out, here I've got that vertical stretch of 2. I didn't really show that in the graph, but it's, you know, I just left the negative because it doesn't talk about reflecting over the x-axis. I've got a reflection over the y-axis with b being negative, and we have that shift to the right because this would start at -2. If you reflect that over the y-axis, it's going to start at +2, and that is our final answer. So that negative b can be tricky, especially when you're trying to come up with your final equation, not necessarily just graphing. I'm Mr. Tarrou. Bam! Go do your homework.